Hi there. Thank you for checking out my presentation, Deep Learning for Spatiotemporal Modeling of Urbanization. I'm Tang Li, a second-year PhD student in the CIS department at the University of Delaware. I'm co-advised by Dr. Xi Peng and Dr. Jing Gao. To summarize our work, we explored the capacity of deep spatial learning for the predictive modeling of urbanization. We treat numerical geospatial data as images with pixels and channels, and enrich the dataset by augmentation. We use UNet model to make pixel-wise regression, and we also investigated the multitask learning probability. Our resulting model can generate end-to-end multivariable urbanization predictions, and in the preliminary comparisons, our model outperformed a state-of-the-art classic machine learning urbanization model, SELECT. Well, urbanization affects the health and the well-being of population across the world. It affected public health, farmland, and climate change, etc. Predictive spatial modeling of urbanization can be a useful tool for effective public health planning and policymaking. Leveraging numerical modeling and classic machine learning techniques, many spatial urbanization models have been developed. For example, the stylized effect models that are based on simplifying assumptions, and spatial interaction-based models such as cellular automata, and the spatially explicit long-term empirical city development model, the SELECT model, is a state-of-the-art classic machine learning model. It was developed using data-driven approaches and newly available historical time series of fine spatial resolution remote sensing observations. The model can make long-term spatial projections of built-up land change, and is also the baseline for evaluating our deep learning model's performance later. We find that deep learning, with its proven capacity to capture complex spatiotemporal phenomena, has not been applied to urbanization modeling. So in this paper, we describe our work as exploring the capacity of deep spatial learning for the predictive modeling of urbanization, and we also explored the augmentation methods for the raw data to enable the deep spatial learning training. And we also explored the comparison of performance level of our deep learning model and a classic machine learning model, SELECT, on producing short-term urbanization predictions. And we also investigated the possibility of multitask learning. Let me first explain our dataset. For our model development, we used the existing dataset that was recently compiled, and it was used to develop the SELECT model. By using this dataset for our model training, we can compare our model's performance with SELECT's performance as a natural benchmark. So in this dataset, the global land area was divided into nearly a million pixels, which is the spatial resolution is 1/8 longitude or latitude degree, which is 14 kilometers at the equator. The whole world is a large image, and the different attributes, for example, topographic context and population counts, etc., as image channels. The 9 input channels are identified by domain experts as influential for urbanization process. They are the distance to the nearest city, the distance to the nearest water body, the mean elevation, the slope range, the land area within a pixel, the population in a pixel in the year of 2000, and the urban land fraction in a pixel in 1980, 1990, and 2000. The target channel is the difference of urban land fraction between 2000 and 2010. That is the urban land change during this time period. To give you a sense of the data, figure 1 shown here some of our input attributes, and A is the built-up land fraction in the year 2000, and B is the distance to the nearest water body, and C is the slope range. And here is our data processing part. We filled water pixels with zeros for each channel, and 20 pixel padding was also applied for the sake of cropping. With each land pixel as the center pixel, we densely sampled near 1 million image tiles for the whole dataset. And the input image has been cropped into the shape 9 by 28 by 28, and the target image has been cropped into 28 by 28. The center pixel also determines the regional belonging of a certain sample. And we also perform the data augmentations by applying like vertical flip, horizontal flip, and also rotation by 90 degree, 180 degree, and 270 degree on both input and output image tiles. Here is our modeling part. We develop the single task learning model first, and we treat the urbanization modeling task as a pixel-wise regression task, which means with the input and the output having the same spatial resolution. The UNet model is a classic deep model for pixel-wise classification. It has been widely used for numerous tasks like biomedical image segmentation, remote sensing image segmentation, etc. We develop a classic UNet model here because it suits our need to make a pixel-wise prediction. And we have to make some necessary modifications to the model architecture to change it into a pixel-wise regressor. Denote the parameter of our model as theta, then the training process of our model can be expressed as the formula shown here. It's basically an optimization process to find the best model parameter to minimize the loss of values. Here the y means the ground truth, and the y hat means our predictions, and the m means the corresponding mask for a certain image tile. And L here means the masked MSE loss, which means during training, all water pixels have been masked out from both the input and target image tiles. Well, we know that during urbanization, the change of built-up land fraction and the change of population are a dynamic couple. Therefore, the knowledge sharing between the modeling of these two tasks may increase the performance of both. To investigate this possibility, we develop a multitask modeling experiment. So the UNet model is also known as a typical encoder and decoder architecture model. So we develop our multitask model architecture by sharing an encoder for both tasks and providing separate decoders for each of the tasks. Then we did comparisons of performance levels of our deep learning model and classic machine learning model select on producing short-term urbanization projections. So here is the results, and our model and the baseline model were evaluated on 4 metrics on both all grid cells and the grid cells with observed built-up land fraction larger than 0 in the year 2010. So the 4 metrics here are mean magnitude of residuals and maximum magnitude of residual and standard deviation of residuals and coefficient of determination. The coefficient of determination is often noted as R square, which means the proportion of the variation in the dependent variable that is predictable from the independent variables. We can see here our method outperforms the baseline model um, all metrics on producing the short-term urbanization prediction. We also compared our multitask learning results with our single task results. As shown in the table, the multitask learning results outperforms the single task learning. So this experiment proved that related tasks will boost the performance of each other, and our method have the capacity to make this kind of modeling possible. And the figure here shows the scatter plot from the single task learning, which is the prediction residuals of all global grid cells on the difference of built-up land fraction. And A is the result of the baseline model, and B is the result of our model. We can see a considerable improvement here. As for future works, we would like to explore that not only spatial, but also extract temporal structure from this kind of spatial temporal data. And furthermore, we would also like to explore the explainable machine learning on our model to interpret the knowledge the model has learned, which will provide our method with much more trustworthiness. As the demonstration shown here, we may investigate the the future importance of our model, and the red color means have positive impact, and the blue color means have negative impact. Thank you for your attention and time. Please reach out if you have any questions. And here are our emails. And thanks again. We're looking forward to hearing from you.